This video is quite mathematical, so if you're not really interested in the mathematics of computing, then you can head on to the next video. It won't stop you from building the CPU. If you are interested in this, then I've got most of the stuff in this video from a book by Roger Penrose called The Emperor's New Mind, and I would suggest chapters 1 and 2 from this would cover a lot of stuff on the ideas about computers and computing, what they can do, what they can't do. Really interesting, really useful, so I would recommend it. So good luck with the video. We started off talking about the Entschuldigung problem. In English this means the decision problem, but we can also call it the halting problem, and we'll see why that is as we work our way through the rest of this video. So let's imagine we had this set of instructions here, and the final instruction ended with stop. So there's no data in here, it's purely the instruction. Now we can code this up using our contraction, and let's say we make 0, 0 equal to 0, the 1, 0 is a 1, 1, 1, 0 is the R, triple 1, 0 is L, and the 4 ones with a 0 is the S. So we could take this set here of instructions, and let's just put them all together without any spaces. So that's them all together without any spaces. And we could use our contraction in order to create a binary number for this. So you can see here that the first 0 becomes 0, 0, and the second 0 there becomes our 0, 0 as well. And then we move on to our R, which is going to be our 1, 1, 0, and we've got our 1, 1, 0 there. So you can see here that we just build up this binary number using this instruction set. So what we could say is that we've generated one particular Turing machine, or it's in effect one particular set of instructions that are in this order. Now we could give the Turing machine a number. In this instance here, what we could do is we could just turn this binary number into a decimal number. So I don't know what the binary number or the decimal numbers here is in this actual instance, but let's just put a random number in. This could be Turing machine number 4715634. So this is a machine that's got this set of instructions, and we can give this machine a particular number. So it's defined, the machine's defined as a one-to-one relation to the number line. So the same goes from all the way from 0 to infinity. You could have a Turing machine number 0, number 1, 2, 3, all the way up to infinity. Now the vast majority of these would be just do nothing of any interest, but some of them would do things that are actually useful. So what we can do is we can start putting it in a kind of shorthand mathematical form. So we could say the T subscript n comma m. So really what we're saying is this is the nth Turing machine, so this is the T subscript n here. So it's the nth Turing machine, but it's acting on the m data points. So that's just been repeated here. So we've got the nth Turing machine acting on m inputs. But now we're going to introduce something called the universal Turing machine. So you could say this is u n comma m. So this Turing machine will in effect be able to mimic every other individual Turing machines. So if you like, you can see that this in fact is an instruction set, and this instruction set can actually be mimicked by a universal machine which can mimic every other Turing machine. So we could say the universal Turing machine n acting on m inputs. So you could say, look at it, and you could look at the nth universal Turing machine acting on m inputs. And whenever you put an input in and you work through the algorithm, you'll get an output, and that output will be p. So you can think of this actually, if you like, in terms of our CPU. So this universal Turing machine is our CPU, and it's able to, we're able to code up any set of inputs or instruction set that we want into this machine, and each and every individual group of instruction sets, we could call that a Turing machine, and it would give us an output, and we can call that output P. Now the interesting thing about this here is, and really the kind of coup de grace, is the fact that this universal Turing machine here will actually have a Turing number as well. So you can actually call this T subscript U. So take your time to get your head round about that. It's quite neat, and it could be quite confusing. Now we've talked about this here, but we're still back at this problem. Is there an algorithm for answering all mathematical problems? Well, let's continue with what we've learned here onto the next page and see if we can answer that. Now, as I mentioned before, we started off talking about the decision problem. Now we can also call that the halting problem. Now what we want to be able to do, we want to see whether there's some Turing machine, we can call it the nth Turing machine, that acts on m inputs, and we want to know if we can find that Turing machine that will tell us whether all other Turing machines will stop at a particular value P, or whether they'll go through an endless loop. So we're looking for the T subscript nm, so that's the nth Turing machine acting on the m inputs, and we want to know that this Turing machine, what it does is it tells us whether all other Turing machines will actually loop, and we can put a little square box as being looping, or whether they stop. Okay, so it's just a magic algorithm that tells us whether all our other algorithms will actually stop and give us an answer, or whether they'll just get stuck in an endless loop. So what we do is we assume that this type of Turing machine actually exists, and we can call it a halting Turing machine. So now we'll have a halting machine we can call h of n comma m. Now what this machine does is, if the nth Turing machine acting on the m inputs is in a loop, so this little square box represents in a loop, meaning it doesn't stop, then it will return a value of 0. But if it does actually stop, then it will return a value of 1. So let's head on to the next page and see how we can use this information. So if we create this little matrix here, then along the top we have all the m's, so that's all the inputs, 0, 1, 2, 3 off to infinity. And down the vertical axis here we have all of the Turing machines, so that's the first Turing machine number 2, 3, 4, and so on and so forth. And that's running from 0 down off to infinity. And inside the matrix are all the outputs. So for example, the fourth Turing machine acting on input number 3 will give us an output of 2. The first Turing machine acting on an input number 1 will give us a value 2, and the first Turing machine acting on an input value 2 will give us a square, which tells us that it is stuck in a loop, that is, it's not halting. Now what we can do here is we can take the Turing machine HNM, and if we multiply that by our TNM, then really what we can do is we can get rid of these squares, and these squares will just become a value of 0. So but doing this multiplication gives us a final machine that we can call QNM, and this here is the little table for QNM. So this process of multiplication is just getting rid of the squares and replacing them in effect with zeros. Now what we're going to do is the some called the Dedekind cut. So if we were to look at just the diagonal entries, so the diagonal entries here are 0, 2, 0, 0 and 5. And if we were to add 1 to every single diagonal entry, then we would have, in this case, we have 1, 3, 1, 1 and 6. So what we can do here is we can write out this mathematically. So we would have the value of 1, because I add 1 on, to the QNN. Now it's NN because we're only taking the nth by the nth value, so that's the diagonal. So that's going to equal our 1 plus our TNM times our HNN. Okay, so it's just making sure that this multiplication here makes sure that the diagonal entries that would have had a box actually now have a 0. So let's continue with this on the next page. So we're saying that that little table that we've drawn out, every single row in it will contain every single computable sequence. But the problem is that it can't actually contain the 1 plus QNN, because every single diagonal entry for the 1 plus QNN is going to be out by a value of 1. Now that's a smart little proof by contradiction using the Dedekind cut. Now go back and have a look at that and have a think about it, because that probably sticks a lot of people whenever they see that at first. It seems almost a cop-out sometimes when you first see it. So this is a contradiction, and it's actually telling us then that this machine HNM, which is the halting machine, cannot exist. It does not exist. So it's really saying is that we cannot create an algorithm that tells us if all the other algorithms will halt or not. Or equivalently, we can say very loosely but quite dramatically and interestingly, there's no master algorithm that can exist that will tell us the answer, if you like, to life, the universe and everything. And as I say, presumably this is why we must assume that the answer 42 is indeed the wrong answer to the life, universe and everything. So a bit of an aside this video, a bit different from the rest of the stuff we've done. So let's get back to designing our CPU. Thank you for listening and goodbye.